Hello, Algebra 2 students. Short video here on the tangent function, Chapter 13, Section 6 in the Pearson textbook. First off, let's define the tangent function as sine over cosine. All right, so I'm going to say the angle in question here is theta, and it's just this ratio of sine over cosine. I want to be able to give exact values for this tangent function, and for that we need to use the unit circle. Okay, so we know the values for sine and cosine. Again, there sine is the y value, and cosine is the x value. So basically you can see that the tangent function is like slope. It's rise over run, y over x. If I wanted to put a delta in there, I get an idea of what it is, the change in y over the change in x. But let's take a look at it. Okay, so just tell me the coordinates here are 1, 0. That's for an angle of 0. For an angle of 30 degrees or pi over 6, the sine is square root of 3 over 2. Cosine, excuse me. Sine is 1/2. That's the one I knew. Okay, and then go to 45 degrees. You got square root of 2 over 2 twice. And finally, for 60 degrees or pi over 3, we have 1/2 square root of 3 over 2. All right, so getting a little messy here. And then finally up at 90 degrees or an angle of pi over 2, we have 0, 1. All right, so you can use these values. Just divide the y value by the x value to get the respective values for the tangent function. So what is the tangent of pi over 6, for example? Okay, the sine of pi over 6 was 1/2. And the cosine of pi over 6 was square root of 3 over 2. And if I simplify that, I think I get something like this. Okay, so you should be able to do that for all the angles, and there are questions in the book involving that. And you could do it in degrees also for the angles. All right, the next topic I wanted to talk about was what does it look like when we graph the tangent function. So of course we could plot these values, x versus y, and get some idea of what it looks like. I could do it on the calculator, of course. I just put in tangent of x. I'm not going to use theta because the theta is there on the button, but it's basically going to interpret it as x. So I graph the function, enter, take a look at the graph, and I get this picture. Okay. Also, I might want to change my window to some trig settings. So I'm going to do zoom number 7, trig. Okay. And now these tick marks actually mean something. I can look at the window settings, and each tick mark is actually pi over 2. 3.14 divided by 2 is 1.57. Okay, so I get this picture here, maybe a better picture on Desmos. I did graph it on Desmos here. And you can see how it repeats itself every pi. Okay, so this is the period of the function. Every pi, it repeats itself. Okay. For the other trig functions, sine and cosine, they're repeating itself every 2 pi. because again, we had to make an entire trip around the circle. But with the tangent function, you can see that we can look at the unit circle and see that we're going to have two places where sine is equal to 0, two places where cosine is equal to 0 in one cycle of 2 pi. So we have to divide by 2 and we get a period of pi. All right, so next thing I wanted to look at was the amplitude. Again, the amplitude is really hard to determine. If I just put a 3 here for the amplitude, it just changes the curvature. Okay. Finally, in the book, they talk about what if I put a coefficient in front of x here? Okay. What happens to the period as I increase the frequency? So the period should get smaller if I increase the frequency. And here you see if I put in a frequency of 2, I've actually divided my period by 2, okay? And it's repeating itself every pi over 2. So again, the formula for period is going to be so I'm trying to get a new page here, is going to be, as they said in the book, t is going to be equal to pi over b, where the tangent function is defined like this. And they could use an x here or a theta for the variable. So this b is going to change the frequency and change the period of the function, just like it does in sine and cosine. Okay, the final thing I wanted to look at was the unit circle definitions review. What does the picture look like for the unit circle? So let's just look at the first quadrant here. All right, between 0 and pi over 2. Kind of a circle there. All right, so first off, we have some angle theta. And if I make a right triangle here, this is where we got the values for sine and cosine from, okay, by doing right triangles, okay, Pythagoras and all that. Those were our proofs. So these values are found on the unit circle, sine and cosine. I always thought of the tangent as being the slope of this terminal ray here. This is the terminal ray. The initial ray, goes down here on the positive x-axis. So that's interesting. It's true. Again, that slope of that line is going to be 0 at an angle of 0. It's going to be 1 if the angle is pi over 4. Good test question. And then undefined, in fact, a vertical line, if we go to pi over 2 up at the top here. Okay, up here, if I drew the angle up to there, it would have an undefined slope. But there's an additional fact here that's pretty interesting, that the tangent, the value of the tangent is actually the length of this line that's tangent out here at x equals 1, 0, 1. Okay, this is another right triangle. Okay, so if we use similar triangles here, it's got the same proportions as the smaller triangle that's inside the unit circle. This red triangle is outside the unit circle. So another definition is the length of this line, as I said, is tangent theta. How can I prove that to you? First off, I said tangent is equal to sine over cosine. All right. or slope, we thought of that. So opposite over adjacent, okay, tangent for the TOA, part of SOHCAHTOA. But in our similar triangle, we have, what is this length down here at the bottom? This length down here at the bottom is just 1. Okay, so the tangent is going to be equal to tangent theta over 1 is in fact the same as this ratio. Okay, so the length of that line outside the circle, I should have done that in red there, the length of that line outside the circle is in fact the tangent because of similar triangles. It's going to have the same ratio as the smaller triangle inside. Tangent theta over 1. So the ratio is the length of this line. Okay, how long does that line get if I go up to a steeper angle? Okay, you can see that I'm way off my graph here. It's getting longer and longer as the angle approaches pi over 2 or 90 degrees. So that's why we see on the graph that it actually goes to infinity. All right, finally, I did put a nice picture of these definitions on It's Learning for my class at Collège de Léman. You can look at the plan for chapter 13 and see it down here, a picture that I borrowed from Wikipedia, and I drew on it a little bit to show that the tangent is this length outside. And then I drew in some things they were missing there. They didn't have the definition of cosine on this picture. And then for pre-calculus students, you can look at the same triangle and come up with a definition or a value for secant as being the hypotenuse of that external triangle. Thank you.